We can never send a probe to scoop up a physical sample of a star. The distances separating us are simply too immense. While a geologist can smash a rock with a hammer, and a chemist can boil a liquid in a beaker, an astronomer has only one source of evidence to analyze: a faint flickering point of arriving light, captured at the bottom of a telescope. To find any meaning in that light, we have to spread it out. By passing a beam of incoming starlight through a glass prism, we divide it into its component colors. This starlight is a dense, encrypted data transmission. It carries the physical secrets of its source star, traveling across the vacuum for millions of years before reaching our lenses. This is the full spectrum of our sun. When we magnify the light to this level, we see that it isn't a smooth, continuous rainbow. It is interrupted by hundreds of tiny, distinct vertical black lines. These dark gaps are called absorption lines. They indicate that very specific, exact shades of color are missing from the star's transmission. Understanding what happened to this missing light and exactly why it was erased reveals the chemical ingredients of the stars. Deep inside the extremely hot, dense core of a star, violent collisions create a continuous, perfect rainbow containing every possible color. As that light tries to escape into space, it must pass through the star's upper atmosphere. This outer layer of gas is relatively cooler, and it acts as a filter. The atoms in that cooler gas are surrounded by electrons that can only sit in specific, strictly defined orbits. When an incoming particle of light, a photon, hits an electron, it can cause that electron to instantly jump from a lower ring to a higher one. These jumps require a non-negotiable amount of energy. Because the energy of a photon corresponds to a precise color, the electron must swallow a specific wavelength of light to make the leap, absorbing that color entirely. The dark lines we see are the atomic shadows of these atmospheric gases. They steal exact wavelengths of light before they can reach Earth. Every chemical element has a uniquely spaced set of electron energy levels. This means every element produces its own unique barcode of absorption lines. This graph identifies the specific dips in the sun's light caused by sodium and hydrogen. Scientists proved these matches by heating known gases in laboratories and comparing their signatures directly to the dark lines in the solar spectrum. In 1868, researchers observed a mystery yellow line in the sun's spectrum that didn't match any known substance on Earth. They named it Helium, after the Greek sun god Helios. It would be nearly 30 years before helium was finally discovered on our own planet. These identical patterns show that the chemical signatures we measure in the laboratory are the same laws operating 93 million miles away. When we look at other stars, the barcodes shift. This comparison shows that Mu Andromedae has much deeper hydrogen lines than our sun, while its sodium signature is barely visible. Across this sequence of different star types, the patterns vary dramatically. Some cool stars even show lines for titanium oxide, the active ingredient in many sunscreen lotions. We might assume this means stars are made of fundamentally different, bizarre materials that have no counterpart on Earth. But the variation isn't due to different ingredients. Our analysis was missing a critical variable: the temperature of the star's outer layers. In 1925, Cecilia Payne realized that an atom's ability to absorb light depends on its electrons being in the correct starting position. That position is determined by the heat of the star's atmosphere. This chart shows how the strength of spectral lines rises and falls as temperature changes. If a star is too hot, electrons are stripped away. If it's too cold, they stay in the ground state. In both cases, the absorption lines disappear, even if the element is still there. By mathematically accounting for how temperature hides certain signatures, Payne proved that the differences in stellar spectra were a matter of heat, not composition. When she corrected for these effects, the true chemical tally emerged. Every star we see follows the same basic recipe, roughly 75% hydrogen and 24% helium. By decoding the missing light, we discovered that the entire universe is built from a single underlying chemical reality: